Good afternoon. This is the Chemistry 241 second hour exam review. I'm going to work through these problems to make sure that you have some shot at understanding them. Again, if you do not understand something that I work through or you need further explanation, please make an appointment to come to me during my office hours, which are printed on the class syllabus, and get some help. Number one, determine the appropriate IUPAC names for the following compounds. This is an aromatic compound. We have a chlorine, a bromo, and the carboxylic acid. This is named as a derivative of the benzoic acid. The carboxylic acid is at the C1 position. Then you number around the ring either one clockwise or one counterclockwise, such that the next substituent has the lowest numbering position possible. Here, if we number clockwise, the bromine is at 2. If we go around the other way, the chlorine is at 4. So we're going around this ring in the clockwise position. 1, 2, 3, 4. So this is 2 bromo, 4 chloro, benzoic acid. Number this one, second one. 1, 2, 3, 4, 5, 6, 7. We have we have a compound that is made up of an aromatic ring and 1, 2, 3, 4, 5, 6, 7 carbons. 7 carbon chain. Since we have more carbons in the chain than we have the aromatic ring is a substituent. Therefore, we name that as a phenyl. We have 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. It's identical. So it doesn't matter which way we count. Do we start 1 here or 1 here? Either one is identical. So arbitrarily, 1, 2, 3, 4, 5, 6, 7. It is a hept. All carbon-carbon single bonds. Ane. Do we have any double bonds? No, not a heptene. Do we have any triple bonds? No, not a heptyne, a heptane. Do we have any pieces of spinach hanging off our longest chain? Yes. What are they? They're a methyl group and an aromatic group. When an aromatic group is a substituent, it's given the designation of phenyl. So this is a phenyl group. We have a single carbon fragment, that's meth for the single carbon, YL for a piece of spinach, methyl. So we got a phenyl group and a methyl group. We need to identify where they are on our chain. Well, if this is C1, there's C2. We have both the methyl group and the phenyl group at C2. Therefore, the position is 2. We list them alphabetically. M comes before P in the alphabet, so it is 2-methyl, 2-phenyl, heptane. Draw the structures corresponding to the following names. 1,3,5 benzene triol. Benzene. Aromatic ring. Tri-3 all OH. We have an aromatic ring, 3 OH groups. Where are they? At the 1, the 3, and the 5 position. 1, 3, 5. 1, 3, 5 benzene triol. 4-phenylheptane. Parent compound. What is it? Heptane. 7 carbons, all connected by carbon-carbon single bonds. 1, 2, 3, 4, 5, 6, 7. Okay, so this is technically it's an octane. Sorry, my apologies. Octane. 1, 2, 3, 4, 5, 6, 7, 8. It's an octane. We have a piece of spinach. What is it? It's an aromatic ring. Where is it? At the 4th carbon in. 1, 2, 3, 4. So this aromatic ring is at C4. 5, 6, 7, 8. So 4-phenyl octane. Name and draw all three, draw three of the potential isomers of the following compound. Name of the compound is bromodimethylbenzene. So on the aromatic ring, you have two methyl groups and a bromine. There are a number of isomers that you can draw. You are only asked to draw three of all of the potential isomers that can be drawn for this compound. So if we draw these, where the bromine and the other two methyl groups are sequentially next to one another around the ring. This is one isomer. It is 1-bromo, 2,3-dimethylbenzene. That is 1, that's 2, that's 3. That's one possible isomer. Another isomer is where we have the bromine between the two CH3 groups. This is 2-bromo, 1,3-dimethylbenzene. If we number around the ring this way, we get a 1,5,6. But if we number 1, 2, 3, 1,5,6 is more than 1, 2, 3. So 1, 2, 3, 2-bromo, 1,3-dimethylbenzene. Another isomer is compound C. This is 2-bromo, 1,4-dimethylbenzene. You've moved a CH3 group to the next position. You move this CH3 right there. So the dimethyl groups are 1,4 to one another. The bromine is at the 2 position, so 2-bromo, 1,4-dimethylbenzene. Other isomers possible. Yes. 3 more isomers possible. You had the compound where the bromine was between the two CH3s. Now you've moved the CH3 one more position around. Compound D is 1-bromo, 2,4-dimethylbenzene. Here, you've moved this CH3 from here to there. This is E, 4-bromo, 1,2-dimethylbenzene. And then F is 1-bromo, 3,5-dimethylbenzene. All of these are derivatives of the compound that would have the general designation as bromodimethylbenzene. Number 4, which of these has either conjugated double bonds or isolated double bonds? These double bonds are conjugated. Why? Because the two carbons that have double bonds to them are adjacent to one another. These double bonds have an sp3 hydrogen and sp3 carbon between those two double bonds. So those have no way of delocalizing across this carbon right there. These carbons can delocalize across 1, 2, 3, 4 atoms because of the presence of the p orbitals on these double bonds. The number of pi molecular orbitals in a molecule is always equal to the number of p orbitals used to construct the pi bonds. There are a number of diagrams in the chapter that talked about how we look at the design and the understanding of the pi molecular orbitals. Sigma molecular orbitals always come from s overlap. The pi molecular orbitals always come from overlap of unhybridized p atomic orbitals. See if I can shrink this down a bit so we can see everything. Number 6, which of these spectra arises which of these following spectra are due to the transition of pi to pi star? The answer here is E. This is a carbon 13 NMR. This is an IR. This is a mass spec. This is a proton NMR. So spectra E here is the spectrum that is due from the electrons moving in the molecular orbitals from the pi to pi star types of transitions. Number 7, circle which of the following compounds would show the longest lambda max wavelength in its UV spectrum. Again, the number of coordinated double bonds, conjugated double bonds, increases the wavelength of the UV absorption. Do we have a double bond? Yes. How many? 1. Are there any other compounds that have more than one conjugated double bond? Yes. Well, this compound has 2 double bonds in it, but are they conjugated? No. This will be more higher wavelength than that, but these are not conjugated. Does B have 2 double bonds? Yes, it does. Double bond here and the double bond there. So the pi molecular orbitals in the C double bond O bond contribute to the lambda max wavelength. We've got 2 double bonds that are conjugated. Longer than this, longer than that. Higher wavelength. This guy, we have these bonds. They're not conjugated. Well, excuse me. They are conjugated. Why? Because there's double bonds, p orbitals, on those carbon atoms. So this is conjugated around the entire ring. So this compound, because of the conjugation possible because of the p orbitals here on each of the carbons of the double bond O, this has 1, 2, 3, 4 possible 4 sites of conjugation. Therefore, all 4 of those double bonds are conjugated. Therefore, this has the largest lambda max, highest wavelength. So, rank the following molecules in order of decreasing lambda max, with 1 being the largest wavelength and 3 being the smallest wavelength. Okay, well, we have to ask the question, do we have double bonds present? Yes. How many? Well, here we have 2 double bonds. Here we have 3 double bonds. This one we have 2 double bonds. Of those, that molecule that has the greatest degree of conjugation of the double bonds will have the highest wavelength absorbance. Do we have any conjugation here? No. We have double bonds, but these are not conjugated because they're not connected. They're not directly next to one another. So this will have the smallest or shortest wavelength. Between these two, do these two have double bonds? Yes. Are they conjugated? Yes. Number 2 here has 2 double bonds that are conjugated. Here and there. Let me see if I can move that down out of the glow. 2 places where this is conjugated. There and there. We conjugate 2 bonds there. What about this guy? This guy has 1, 2, 3 double bonds. Are they conjugated? Yes. This is conjugated because this is adjacent to that. Is this carbon adjacent? Yeah, it is. So these 3 double bonds are all connected to one, conjugated with one another. Therefore, this will have the largest wavelength, the largest lambda max. This will be next largest. This will be the smallest. Move this down here. It's probably better. Identify which substances are aromatic and which are anti-aromatic or non-aromatic. Write your answers beneath each structure. Is this aromatic? Yes. Why? Don't we have all 3 double bonds immediately adjacent to one another? Yes. Does this CH2 conjugate with the aromatic ring? Yeah, it does, but it's not aromatic because of this. It's aromatic because of the ring. Okay, is this aromatic? Let's assume one. We have to have four things being true. One, is the molecule flat? Is the molecule cyclic? Is every atom in the molecule sp2 hybridized? And are there multiple of 4n plus 2 pi electrons? Let's make the assumption that all of these are flat. Make the assumption that all of these are cyclic. Do we have every atom here involved in an sp2 kind of hybridization structure? No, we don't. Is that oxygen sp2 hybridized? No. Is that nitrogen sp2 hybridized? No. So this guy is not aromatic because this oxygen is not involved in an sp2 hybridization kind of structure. This guy, if it was involved in a double bond, could we have could we make this aromatic? Yeah, but since it's not aromatic. Not aromatic. This guy, let's assume it's flat. Let's assume it's cyclic. Is every atom involved in sp2 hybridization? No. Do we have available pairs of electrons that we could get every atom involved in conjugation? No. Is that sp2? Yes. sp2, 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 sp2. sp2? No. That's sp3. Is that sp2? No. Is this aromatic? It's not aromatic. This guy is aromatic. Is that guy aromatic? Let's make the assumption that it's flat, it's cyclic. Do we have all the atoms involved in sp2 hybridization? No. But do we have electrons here that could be put into an orbital that is perpendicular to these other electrons? Yeah. So we have 2, 4, 6 pi electrons. This system is aromatic. Is this guy aromatic? Let's assume that it's plain. Let's assume that it's planar. It's cyclic. Are all the atoms involved in sp2 hybridization? No, these nitrogens are not. But what if we allow this pair of electrons to go into a p orbital? Well, we would have to put those electrons into a p orbital too, such that that could be potentially overlapping with the p orbitals there. We would have 2, 4, 6, 8. This is not aromatic. Number 10, which one of these compounds will react as a diene in a Diels-Alder reaction? Diels-Alder reaction. The diene has to be able to get into an S-cis conformation. Are the double bonds in this structure in this orientation? No, if we actually look at it. Since this double bond is part of a ring, the ring cannot bend itself such the double bond is right there and it gets into that conformation. Is this dying in the S-cis conformation? Well, the S-cis conformation requires that these two double bonds be, the carbons on these double bonds be right next to one another. Are either of the ends of the double bonds right on adjacent carbons? No. D. Again, we'd have to have this double bond here and in this position. Since it's part of the ring, we can't delocalize around the ring. So D, it can't happen. Here in C, we have this bond down, but this is a carbon-carbon single bond. This carbon can rotate, double bond can get into this position, so C can undergo a Diels-Alder reaction. There's number 17. This is indene. You can have the electrons either in the ring, either this position, or we can flip them around. So this is 1, 2. This is this guy, or the double bond could be there. So there are 3 resonance structures. Hint that there were only 3. It says 1 point each, 3 points total. That should give you a hint that there were 3 resonance structures. One involves the aromatic double bonds being in this position. One involves the other double bonds being in this position. This and this are identical. The other resonance involves the double bond flipping from there to there. Number 12, propose the structure for a substituted aromatic compound as the following data. Molecular formula C8H9Br. It has an aromatic ring and a carbon chain. It has the following proton, carbon 13 NMR. So you know you have an aromatic ring. I've told you that, and a carbon chain. So the aromatic ring comes up with C6. So C8H9 Br, we've taken up immediately C6. 6 carbons. You have 2. I've told you it's a carbon chain. And your proton NMR from 4 to 7, you don't have anything. So it is not a double bond. There is nothing from 4 to 7. It's not a triple bond. So it is a total hydrocarbon-like environment. So this C2, we see in the proton blow up. Here is the full proton NMR. We see something a little bit above 1, something about 2.6, 2.7, and then multiple peaks down here above 7. This here, the blow up of that. Each of these hydrogens, each of these peaks is integrating two hydrogens. So on your ring, you have only 2 kinds of hydrogens, but each one is integrating such that each peak represents 2 hydrogens. So we're saying we have 4 hydrogens total on the aromatic ring. C6H4. That leaves you with C2H5. C2H5 is supported by the CH3, the triplet quartet pattern. The triplet quartet says CH2CH3. So if we have the aromatic ring, C2H5 is CH2CH3. So you've got an aromatic ring with an ethyl group on it. Would that give you that splitting pattern and that integration? No, it wouldn't. Here is one kind of hydrogen, here is one kind of hydrogen. We have 4 total hydrogens, but we're seeing 2 peaks. Each peak integrates to 2 hydrogens. So we're saying we have some sort of substitution on our aromatic ring such that we only have 2 kinds of hydrogen. Well, what's the only element we've not accounted for in our formula? Bromine. So we have to have a bromine position. We've taken care of all the other carbons. We've got C6 and then a CH2, CH3. That's 6 carbons. The only other thing that we haven't accounted for is our bromine. This kind of symmetrical substitution pattern. We see these 2 tall peaks and we see these shorter outer ones. Is characteristic of a para 1,4 substitution pattern. Will this compound fit the data that we have? Yes. CH3 split into a triplet. CH2 into a quartet. So the triplet quartet pattern, CH3, CH2. We don't have any other hydrogens, CH3, CH2. So there's 2 and 3, and then there's 4. 2 and 3 is 5, and 4 is 9. We've accounted for 9 hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9 accounts for that. Does it account for a splitting pattern? Yeah, it does. These hydrogens are identical. Those hydrogens are identical. The hydrogens here are both 1 away from this carbon. They're also 2 away from this guy and 2 away from that guy. These hydrogens are different than these. Both of these hydrogens are attached to carbon that are both attached to the carbon as the bromine. These are all both 1 away from the carbon that's immediately next to that carbon right there. So we have that kind of splitting pattern, the para splitting pattern. Let's look, was this the only data? No. We have carbon-13 data. Carbon-13, we have 1, 2, 3, 4, 5, 6. We have 6 carbons showing up, but the numbers above these says this peaks represent 1 carbon. Both of these represent 2. So 1, 2, 3, 4, 5, 6, 7, 8. Don't we have 8 carbons? Yes, we do. C8. These in the 120 to about 140, 150, these are your aromatic carbons. We have 1, 2, 3, 4, 5, 6. These carbons down about 40 and about 29 are your CH2, CH3. CH2, CH3 are hydrocarbon-like environments. They're way upfield towards TMS. That was number 12. Number 13, rank the following compounds in order of reactivity towards electrophilic aromatic substitution. You're looking here at basically aromatic ring is present in each compound. This guy has a fluorine directly substituted on the aromatic ring. This guy has a methyl group on the aromatic ring. Number 2 has a fluoro on the methyl group attached to the ring. Here we are looking at 1 least reactive. 2, second, and 3, most. So we're looking at how fast these react towards electrophilic aromatic substitution based on basically what's attached to the ring. Halogens directly attached to the ring. They are ortho-para directors. So these dump electron density into the ring. These activate the ring. So since this fluorine is directly attached to the ring, this is most reactive. The second most reactive is this guy. It has a fluorine attached, it has a fluorine present, but the fluorine is not directly attached to the ring. It's attached to the methyl group. This does dump electron density into the ring, but not as strongly as this does because this is directly attached to the ring. That fluorine is directly attached to the ring. This fluorine is attached to a carbon that's attached to the aromatic ring. This is, compared to this guy is not as reactive as this guy is. This is the least reactive. The CH3 is an ortho-para director. It is a ring activator, but it is not as strong as a ring activator as the halogens are. Number 14, identify each of these, the OCH3, the cyclopentyl, and this cyclohexenol. Identify each of these groups, this guy, that guy, and that guy, as either deactivators or activators. Do they dump electron density in the ring, or do they donate electron density, or do they pull it out? And ortho-para or metadirectors. Your choices were activator or deactivator. This is a ring activator because the electrons are directly attached to an oxygen which is directly attached to the ring. It can donate those electrons into the ring. Again, alkyl groups are electron donators. They donate electron density into the ring, therefore they are activators. The carbonyl group immediately attached to the aromatic ring is a ring deactivator. Because that carbon is electron deficient, it pulls electron density out of the ring, making it less nucleophilic. Those things that are activators are ortho-para directors. So since this guy's an activator, it's an ortho-para. This guy's an activator, it's ortho-para. This guy is a ring deactivator, it's meta. You had to choose 6 of these reactions. You could have chosen any 6. I will show you the answers to each. Let's start this down a little bit so it's not in the glare. Number 15, 15A. This is a diene. This is a dienophile. This is a Diels-Alder reaction. There, here. We form the double bond and the trans stereochemistry. When the alkene and the diene act, they add facially. So this is going to be down, this is going to be up. These are on opposite sides. Number B. This is 1,4 addition of bromine. Higher temperatures. 1, 2, 3, 4, or 1, 2, 3, 4, depending upon how you want to label it. The bromines add 1,4 at high temperatures. Number C, we're not adding Br2, we're adding hydrogen. HBr can add here or there. We can, since this is a conjugated double bond, Markovnikov addition says the hydrogen adds to the most substituted double bond. I mean, the least substituted double bond. There or there, or excuse me, is the most substituted double bond. Therefore, the hydrogen does not add there. It adds either here at this end or there at that end. For the product, let's assume that the hydrogen adds here. Therefore, we have that conjugated double bond. The tertiary carbocation is the most, okay, what am I doing? This tertiary carbocation is the most stable, so the bromine adds there. So we have 1,4 addition and 1,2 addition. (15D), provide the major organic product for the reaction shown. This is a Friedel-Crafts alkylation reaction. Once we react this alkyl chloride with aluminum trichloride, we form that carbocation. That is the primary carbocation. That is not stable. We have a hydrogen right there. This can undergo a 1,2 hydrogen shift and get to a tertiary carbocation. Now this aromatic ring reacts with this tertiary carbocation to give you that species, right? The final product right there. (15E). The halogen, the sodamide or the potassamide reaction should say the production of benzene. So you add the ammonia group to either the position where the bromine was or the adjacent position, i.e. it goes through some sort of proposed triple bond species. So the NH you could add here or there, getting you the para, or the meta derivative. F, we are reacting this cyclic system with potassium permanganate. The positions that are direct, those carbons that are directly attached to the aromatic rings are most most susceptible to oxidation, these benzylic positions. So the potassium permanganate chews open these carbon positions right here that are immediately attached to the aromatic ring to give you the corresponding carboxylic acid. Therefore, you have the benzene dicarboxylic acid as your product. G, H2, platinum. H2 and platinum says we're adding hydrogen to a double bond. This is done at 2,000 psi. Again, regular hydrogenation reactions are maybe done at 1.5, maybe 2 atmospheres. But since we're doing this at 2,000 psi, we're reducing all the double bonds of the aromatic ring. So we go from this dimethylbenzene down to the corresponding dimethylcyclohexane. The key conditions here is this 2,000 psi. You're having to really whack this thing to get the hydrogen to absorb and reduce all the double bonds in your aromatic ring. H, NBS, with a benzoyl, with a peroxy material, benzoyl peroxide. NBS brominates immediately alpha to the ring. So it adds a bromine to this benzylic position, giving the monobromo. HI, J, okay. I. Hydrogen with palladium reduces down the double bond from the C double bond O to the CH2. However, it also reduces down the nitro group down to the amino group. So you have a direduction here, the C double bond O down to the CH2 and the nitro to the amino. Again, this position is activated towards reduction because of its position with respect to the double bonds. It can conjugate. It makes this more like a carbon-carbon double bond. Adding the hydrogen across gets you down to the alkane, reducing this nitro group, which is very reactive, down to the amine. J, sulfur trioxide and sulfuric acid. This is a sulfonation reaction. So CH3 is a activating group. It's a weak activating group. It can go either ortho para. So this position is identical to this one. So we can add either here or here, which is ortho, or it could add para 1,4. So you have these two products. And last one. Starting with toluene, how would you synthesize metafluorobenzoic acid? The hint was, starting with toluene, how do you get here? The hint was it's a two-step process, so you can't do this all in one step. So since you're starting with this, you have to say, okay, well, if I have this, this is going to direct anything that I add to the ring either to an ortho position or a para position. But I don't want whatever this is going to be ortho para. I want it to be meta. So we need to change this into a meta director. We do that by oxidizing this methyl up to the corresponding benzoic acid. This carboxylic acid group is a meta director. So you use the fluoro to EDABF4, adds the fluorine to the aromatic ring, but adds it in a meta position as your benzoic acid group is a meta director. So you end up with fluorine either here or here. Doesn't matter. Each one is identical. That is the review for the second hour exam for Chemistry 241. If you have any questions, please make an appointment to come see me during my office hours and we can get your questions answered. Have a good break.